What if I told you there's a new kind of artificial intelligence out there that doesn't just learn from data, but from the very architecture of our own brains? Well, today we're talking about spiking neural networks. And believe me, they might just be the answer to one of the biggest and quietest problems in AI today. Okay, so we all love what AI can do, right? From generating incredible art to helping doctors, it's amazing. But there's a hidden cost. Behind the scenes, these massive AI models are incredibly thirsty for energy. It's a huge and honestly an unsustainable power problem that's happening completely out of sight. Take a look at this number. 1.1 million nanojoules. Now that's how much energy a standard AI needs just to recognize a single, simple, handwritten number. A tiny task. But when you think about the billions of operations these systems do every single day, that energy cost, it adds up fast. As AI gets more powerful, its environmental footprint gets bigger right along with it. And this is where things get really fascinating. Look at this gap. On one side, you've got our traditional AI, which is basically always on. It's firing everything all the time for every single calculation. But on the other side, you've got the human brain. The most complex computer we've ever found, it runs on about 20 watts of power. That's less than a dim light bulb. This huge efficiency gap got researchers thinking, wait a minute, can we build an AI that works more like that? And that very question leads us right to the brain's secret weapon. It turns out the key to its incredible efficiency isn't just what it's computing, but how it's communicating. It uses a method that's sparse, it's events-driven, and it is just unbelievably powerful. So let's look at the original blueprint, a biological neuron. See, unlike the artificial neurons in most AI today, this little cell doesn't just send out a constant flood of information. Nope, it waits. It actually listens to its inputs. And only when it reaches a certain threshold, bam, it fires off a single, sharp electrical impulse, a spike, to its neighbors. And that right there is the whole idea behind a spiking neural network, or SNN. It's all about the spike. It's an event. Nothing happens, no energy gets used until a neuron actually fires. This means all the computation is sparse. It only happens when and where it's absolutely necessary. This whole event-driven thing, that's the secret sauce. That's what makes them so incredibly energy efficient. Okay, so taking that beautiful, elegant idea from biology and turning it into real working technology, how do you actually do it? Let's take a look at how you actually build one of these things. At a high level, the whole process is a three-step dance. First, you have to encode your data. You have to take something like the pixels in a picture and translate it into a language the network understands, which is patterns of spikes over time. Then you process it. Those spikes ripple through the network layer by layer. And finally, you have to decode the result. The final pattern of spikes at the very end gets translated back into something useful, like, yep, that's a picture of a cat. But of course, it's never quite that simple, is it? Building an SNN that actually works well is kind of like solving a puzzle. Every single choice you make, from how you encode the data to what kind of neuron you use, comes with these really critical trade-offs between things like accuracy, speed, and how much energy you're going to use. So that very first choice is a big one. How do you turn your data into spikes? Well, you've got a few options here. You could use something called rate coding, where basically a brighter pixel just fires more often. It's simple, it's pretty robust. Or you could go with temporal coding, where the exact timing of a single spike carries all the information. Super fast, but a little sensitive. And then you have even more advanced methods, like sigma delta, which are crazy efficient for streaming data, but man, they require some careful tuning. And after that, you have to pick your neuron model. And just like in real biology, there's a whole zoo of them to choose from. You've got the simple, cheap, and reliable leaky integrate and fire, or LIF model. That's kind of the workhorse for a lot of these networks. Then you can get more complex with models like ADX or Izhikevich, which can mimic fancier brain behaviors like bursting. And way at the other end of the spectrum, you've got Hodgkin-Huxley, the gold standard for being biologically accurate, but it's just way too slow and expensive for most practical uses. So after all those decisions, can an SNN actually compete with the big guys? Well, the results are, honestly, they're stunning. On that same digit recognition task, a standard AI gets 98.23% accuracy. A really well-designed SNN, it hits 98.10%. I mean, come on, that's pretty much identical. This is huge because it proves you don't have to give up performance to get all that efficiency. But this is the real payoff. Remember that crazy energy number from before for the traditional network? Over 1 million nanojoules. Well, the SNN that got almost the exact same score? It used less than 96,000 nanojoules. That is more than 10 times more energy efficient. We're not talking about a small improvement here. This is a total game changer. So this incredible efficiency, it's not just a cool number on a chart. It's actually making totally new things possible out in the real world, in places where low power and high speed are everything. And the inspiration just keeps coming straight from the source. This is just amazing. Scientists can now actually look at the spike patterns firing in a rat's hippocampus, that's the part of the brain for navigation, and they can see the exact path the rat is thinking about taking before it even takes a single step. And this is where it gets really, really cool. Taking that idea directly from the rat's brain, engineers built an SNN that does the same thing. For a robot arm, the network plans a smooth, efficient path to a target, dodging obstacles along the way, all by processing these patterns of spikes. It is a literal translation from biology to robotics. And that's just one example. SNNs are really perfect for any place where power is tight and time is critical. We're seeing them in special neuromorphic chips, like Intel's Lohi, that are built from the ground up to work like a brain. They're popping up in medical wearables, meaning your watch could analyze your heart rhythm for days without a recharge and without sending your private data to the cloud. And it's a huge deal for Edge AI, which is all about putting smarts on devices that aren't always connected to the internet. So, what does this all mean for the future of AI? Where are we headed? It really feels like we're at this turning point, moving away from just brute force computing and towards something, well, something a lot smarter. I think this quote from Geeks for Geeks really nails it. SNNs aren't just a tiny step forward. They are a totally different way of thinking about computation itself, a way that's more efficient, more dynamic, and a whole lot closer to how intelligence actually evolved here on Earth. And that leaves us with one last big question to think about. For the last 10 years or so, the race in AI has been all about building bigger and bigger and bigger models. But maybe we've been running in the wrong direction. Maybe the next giant leap for AI isn't about being bigger, but about being smarter and a whole lot more efficient. Thanks for joining me.